Good day, everyone. In the previous episode, we briefly analyzed a displacement time graph, the motion of a particle in a straight line. Another motion graph worth analyzing is a velocity time graph. How do we interpret this type of motion graph? Just hang on, watch and learn. The question is, a traffic enforcer starts his motorcycle and chases a van that overspeeds. Question is, which velocity time graph in the figure is correct? Justify your answer. We assume that the van and the motorcycle are in straight line motion and that the motorcycle cop is able to catch up with the van at the specified time of 10 seconds. So, in this type of graph, velocity versus time graph, we are able to get some bits of information with regard to the motion of the two bodies. For example, referring to the VT graph in option A. Such information like what the velocity of the body is at a given time. So the answer is, at time t equals 5 seconds, we say that the velocity of the van is 20 meters or positive 20 meters per second. Another information is at what instant the instantaneous velocity of a body is. So we say the motorcycle is traveling at 20 meters per second at exactly t equals 10 seconds. So this information can just be read off directly from the graph. But other important information about the body's motion can also be determined by calculation, such as the distance traveled or the displacement of the body at any given time interval, as well as the average acceleration or even the instantaneous acceleration of the moving body. And we shall talk about them in more details in just a short while. The third information that we can glean from a velocity time graph is the distance or the displacement of a body. How far the body has traveled within an elapsed time. Like in the graph for option A, we can calculate the distance traveled with the van in 10 seconds. So this distance is just equal to the area bounded by the horizontal graph line and the time axis. This area is that of a rectangular polygon, which in geometry is equal to the product of the length and the width. Or this can be similar to finding the distance traveled equal to the change in the time or the elapsed time multiplied by the constant velocity Vx. Right? So when we multiply the velocity of the van, which is 20 meters per second, by the time elapsed of 10 seconds, we will get the distance traveled equal to 200 meters. And since the van is moving with a constant velocity, we say that its average acceleration is equal to 0. right? Within the same time interval, delta t equals 10 seconds, we also calculate for the displacement of the cup's motorcycle, all right? And this distance traveled by the cup is just equal to the area of the triangle shaded blue. And this is equal to 1 half times the change in the velocity and the change in time delta t, all right? So when we substitute the quantities, we get d is equal to 1 half multiplied by the change in velocity, which is 20 meters per second minus 0 meter per second, and that's multiplied by the delta time or delta t, 10 seconds minus 0. So the distance traveled by the cup or by the motorcycle is just equal to 100 meters. So this means that the cup has not yet caught up with the van. It's still 100 meters behind the van. All right? 200 meters, which is the distance traveled by the van, compared to the distance traveled by the cup, at the end of 10 seconds, we say that uh, the motorcycle is still 100 meters behind the van at that very instant, uh, 10 equals, t equals 10 seconds. And calculating for the motorcycle's average acceleration, we just use the slope formula of a velocity time graph, right? So, the formula for the slope of a velocity time graph, right, is just to divide the change in the velocity delta v by the change in time delta t, right? So when you substitute within a period of 10 seconds, we have the change in velocity 20 meters per second minus 0. That's divided by 10 seconds, and we will get the value for the acceleration of the motorcycle equal to 2 meters per second squared. All right? So within 10 seconds, this acceleration of the motorcycle is kept constant. And at exactly 10 seconds, the motorcycle has a velocity or a speed equal to 20 meters per second, the same as that of the van, but the motorcycle has just traveled a distance of 100 meters. All right? So he has not yet caught up with the van. For the BT graph in option C, the same displacement or distance traveled by the van as what we got in option A, which is 200 meters. The distance traveled by the cop or motorcycle in 10 seconds is also equal to the area of the nearly triangular polygon shaded blue. All right? Now, it is pretty obvious that this area is less than the area we got for the right triangle in option A. Okay? So we say the motorcycle has not yet caught up with the van at this time t equals 10 seconds. But his acceleration is not constant. All right? From the beginning or from time equals 0, its acceleration is increasing. And his average acceleration, if the graph line is diagonal or diagonal straight, would also be equal to 2 meters per second squared. But since the graph line is a curve, right? The graph line is a curve suggesting a varying acceleration. We can consider 2 meters per second squared, all right, as the instantaneous acceleration of the motorcycle at an instant approximately t equals 5 seconds, which is half of the time interval 10 seconds. Okay, so we are using the concept of averaging. All right, so just like in option A, this graph in option C doesn't represent a complete scenario of the given situation. For option B, the distance traveled by the van is still equal to 200 meters. And the distance traveled by the cup is just equal to the area of the right triangle shaded red in the graph. And this distance traveled by the cup can just be determined, all right, using the formula 1/2 the change in velocity delta b and the change in time delta t, all right? So that's just analogous to getting the area of this right triangle, which is 1/2 base times height, all right? And when we plug in the quantities into this formula, we infer that the final velocity of the motorcycle V2, okay, in the graph at exactly 10 seconds is equal to 40 meters per second. So when we substitute in this formula, we have 1/2 multiplied by 40 meters per second minus 0 and multiplied by the delta t, which is 10 seconds minus 0. So, right? Using our math, we will get the value for the distance traveled by the cup equal to 200 meters. All right. So therefore, um, this means that the motorcycle cup has already caught up, okay, with the van at exactly 10 seconds. All right. Because their displacement are both equal to positive 200 meters. All right. And this happened at an instant equal to 10 seconds. But take note, at that instant, 10 seconds, the motorcycle cup is traveling at a much faster velocity, equal to 40 meters per second. All right. Because from the very start at time 0 until 10 seconds, all right, we emphasize that the motorcycle cup has been constantly accelerating, right? And in delta t equals 10 seconds, he was able to travel the same distance that the van has covered. So that means the motorcycle has already, okay, at the same displacement as the van. He has already caught up with the van and still continuously speeding up, All right, but that is no longer uh, given in the graph. All right. Okay, so um, from the time the cup started to accelerate from rest with a constant average acceleration equal to uh, 4 meters per second squared. All right. So that acceleration of the cup, okay, as shown here, is determined by just dividing the change in the velocity 40 meters per second minus 0 divided by the time interval 10 seconds. All right. So what we got is 4 meters per second squared. All right. So it appears that this graph shown in option B completely illustrates, all right, the given problem situation. For option D, the distance traveled by the van is still equal to 200 meters, while the area of the nearly triangular polygon shaded blue, all right, represents the distance traveled by the motorcycle. All right. And we take note that this distance is less than 200 meters. All right. Because the area bounded by the curve and the time axis is less than that, what we got in option B. All right. The area shaded red. Okay. So in short, the motorcycle has not yet caught up with the van in 10 seconds. But we can also consider its acceleration. All right. If that graph is not a curve, okay, if it is a straight diagonal line, we can also say that the acceleration on the average of the motorcycle is also equal to 4 meters per second squared, as shown in this working. All right. But since the fact that it is not straight diagonal line, all right, suggesting that the acceleration of the motorcycle from the very start time equals 0 until the time 10 seconds, the acceleration is in fact increasing. All right. But such average acceleration, 4 meters per second squared, can be inferred to be the instantaneous acceleration of the motorcycle at exactly 5 seconds, which is half of the time interval 10 seconds. Right? But just like in the graphs for options A and option C, this one also does not correctly represent, okay, uh, the given scenario or the assumed scenario in the question. So, for our final answer to this question, okay, it is clear that among the four options, it is the graph in option B that correctly depicts, all right, the situation given in this question. So, option B is our best answer. All right. So that completes our video tutorial for this episode. Till the next video lesson, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.